Now let's move on to next question, 1b. For the same question in 1a, is the average age of the US population significantly different from 35 at the 1% level? Compared with question 1a, the only difference here is that for 1b, we adopt a different level of significance. It dropped from 5% to 1% level. Now let's follow through the 7-step procedure. First step, we set up null hypothesis and alternative hypothesis. The null hypothesis states that the mean of the population is not significantly different from 35. And the alternative hypothesis says that the mean of the population is significantly different from 35. So still a two-tail test. Second step, we set up alpha. Alpha now is set at 1% level. Then we're going to find out what are the critical values that correspond to 1% alpha. So we look up, if we evenly split 1% in two tailed, so 0.5 in lower tail and 0.5 in upper tail, and that leaves the 49.5% from the mean up to 0.5% corner. So if you look up the normal table, find a probability closest to 49.5%, and you read the table backwards, you can find the critical z-score. And those are the positive and the negative 2.58. And these two critical z-score delineate entire z distribution into a non-rejection region in the middle and two rejection regions at the corner. So now we have this set up. We can deal with our sample. We're going to convert our sample mean into a statistic z-score using this formula. From the last question, we know that the z-score is 2.24. Now, next step, we need to compare the sample mean test statistic z-score with critical value, the critical z-score value, to determine where the sample mean falls, for the rejection region or non-rejection region. 2.24 is smaller than 2.58, so it falls to the left of 2.58. In other words, it does not fall in the rejection region. So from this step, we already know that the sample mean in our hand is not a real event for the given null hypothesis when we set alpha at 1% level. So to this point, we already know that for this question, we cannot reject the null hypothesis since the sample mean which convert into a z-score is a 2.24, it does not fall in the rejection region. So it's not a real event for the given null hypothesis. So well, we know, but still we need to calculate the p-value to see how unrare it is for this particular sample mean for the given null hypothesis. So we're going to go to calculate a p-value for this question too. Now again, we enlarge this corner to see it more clearly. This is the critical z-score 2.25, and the sample mean test statistic z-score 2.24 fall to the left of the critical z-score and forming this larger corner. So the p-value for this question will correspond to this larger corner. We go to the normal table, we find that the probability for z-score to fall between 0 and 2.24 is 0.4875. And in a normal distribution from a mean up to this 2.24, that's where the 0.4875 located. And from this, we can easily calculate the size of this corner to the right of this orange line. which is we subtract 0.4775, 0.4875 from the 0.5, which give us 1.25. 1.25. And also we know from the previous discussion that in a two-tailed test, the p-value is double the size of one corner. So the p-value is 2 times 1.25 is 2.5%. Now 2.5% is way larger than the alpha we set up for this question. In this question, we set up the alpha at 1%. This means that those events that occurred at the 1% level or lower will be regarded as real events for the given null hypothesis. But we realize that the probability for the sum of mean 37.5 happened if is at the 2.5% level. Therefore, this level is much higher than the 1% level that we define as the probability for real events. Therefore, we know that if the population mean is at 35, the probability of obtaining a sum of mean 37.5 is higher than the 1%, which is the standard that we set for real events for the given null hypothesis. Therefore, we know that the sum of mean 37.5 is not real event for the given null hypothesis for this question. Therefore, we would have no reason to reject the null hypothesis. So we make a decision that we fail to reject the null hypothesis, and we conclude that the published mean is not significantly different from 35 at the 1% level. As you can see, that the difference between this question 1b and the last question 1a is that alpha for this question is much lower. We have a much more rigorous standard to reject the null hypothesis. As we discussed previously, when the alpha is very low, that means that for the same sum of mean, you would have a harder time to reject the null hypothesis because the rejection region becomes much smaller. For the same sum of mean, it may not be a real event for the given null hypothesis when the alpha level becomes small and the rejection region also becomes small. So this is question 1b. Now question 1c. For the same question in 1a, is the average age of the U.S. population significantly higher than 35 at the 1% level? Now for this question, from the way that the question is asked, you can realize that this should be a one-tailed test because it does not ask you whether, it no longer asks you whether the average age of the U.S. population is significantly different from 35 anymore. It asks you specifically whether it is higher than 35. So that really indicates a one-tailed alternative hypothesis. So let's use a 7-step procedure to conduct this test. First, we set up null hypothesis and alternative hypothesis. Null hypothesis still states that the average age of the U.S. population is significantly different from 35, but the alternative hypothesis states that the average age of the U.S. population is significantly higher than 35. Okay. So this is a one-tailed test, specifically is upper one-tailed test. We bet that the real event may happen in the upper tail. Now let's set the alpha at 1% level because this is given specifically by the question. Now third step is we find out the critical value that corresponds to this 1% alpha level. Now, in order to increase the probability to reject the null hypothesis, we place all 1% in the upper tail. So this we only have one rejection region that occur in upper tail, we'll place all 1% in the upper tail. Then we are going to go to the normal table to look up a probability closest to 49% to find the critical z-score. And it turns out that the z-score, critical value z-score, is positive 2.33. And this critical z-score delineates the entire z distribution into a rejection region in upper tail and a non-rejection region for the rest of the distribution. Okay, now with this setup, we can deal with the sample in our hand. We can convert the sample mean into a z-score, test statistic z-score. So it's the same calculation and give us a sample mean test statistic z-score 2.24. Now 2.24 fall to the left of critical z-score 2.33. It's there, so it does not fall in the rejection region, so it will fall in the non-rejection region. And so from this point, we already know that for this question, we have a sample mean that does not fall in the rejection region. It's not regarded as a real event for the given null hypothesis. Therefore, for this question, we should not reject the null hypothesis. But still, we'd like to find out how non-real it is for this particular sample mean for the null hypothesis. Therefore, we need to calculate the p-value that corresponds to 2.24. So we enlarge this corner. This z-score 2.24, 2.33 is a critical value. The test statistical z-score 2.24 fall to the left of 2.33. The p-value corresponds to this corner cut off by the orange line. So we look at the normal table. We find out that the probability for z-score fall between 0 and 2.24 is 0.4875. And that means that in this distribution from the mean up to the orange line 2.24, we have the probability 0.4875. So we can easily calculate the size of this corner, which is 1.25. Now, we know that 1.25 is the size of this upper corner. In a one-tail test, the p-value is the size of that one corner. So from this one, from this value, we can also calculate the p-value. P-value is the 1.25. 1.25 is larger than 1%, which is alpha. So from this conclusion, we can make a decision that we cannot reject the null hypothesis, and we fail to reject the null hypothesis, make this decision, and we conclude that the published mean is not significantly higher than 35 at the 1% level. That means that if the published mean is 35, the probability of obtaining a 35.7.5 is very high. So that's why we cannot reject the null hypothesis. So this is an example that illustrates how we conduct a upper one-tail test. Question 1D. If a sample of size 25 is taken, and the sample mean is 33.3, if the average age of the US population is significantly younger than 35 at the 5% level. So this is an example that will tell us how to conduct a lower one-tail test. First, we set up null hypothesis and alternative hypothesis. Null hypothesis states that the average age of the US population is not significantly different from 35. And the alternative hypothesis says that average age of the US population is significantly younger than 35. And we put up the 5% alpha level, and then we need to find out the critical z-score that correspond to 5% alpha in one-tail test. Again, for this question, since we have a lower one-tail alternative hypothesis, we place all the 5% probability rerun in the lower tail to increase the probability to reject the null hypothesis. So we place all 5% in a low tail, and if we have 5% in the lower tail, so we would have 45% from mean up to the 5% lower tail. So we look up the normal table, find a probability closest to 45%, and to determine the critical z-score, it turned out to be negative 1.65. So with these first three steps ready, we have this set up, so we can move on to deal with the sample mean in our hand to convert it into a test statistic z-score. So now we have this negative 1.65 delineate the entire z distribution into a rejection region at the lower corner and the non-rejection region for the rest of the z distribution. Now let's calculate our test statistic z-score. Use same formula, but this time since the sample mean is 33.3, okay, so the sample mean test statistic z-score is negative 1.7. Negative 1.7, compare that with the critical z-score negative 1.65, it falls to the left of negative 1.65. Therefore, we realize that the sample mean falling the rejection region in the lower tail. So it is a real event for the given null hypothesis. So for this question, we need to reject the null hypothesis. Again, we need to find out how rare it is for this sample mean for the given null hypothesis. That's why we need to move on to step number 6 to calculate the p-value. So we enlarge this corner, the lower tail, and realize that the sample mean related test statistic z-score negative 1.7 fall to the left of the critical value negative 1.65. So we have a green corner. The p-value is closely related to the size of this green corner. So we need to calculate the size of this green corner. So you'll go to the normal table to find a z-score negative 1.7. So you know the probability for z-score fall between the 0 and negative 1.7 is 0.4554. That means in a z distribution from the mean up to negative 1.7, the value is 0.4554. And from this, we know it's easy to calculate the size of this green corner and subtract 0.4554 from 0.5. So the size of the green corner is 0.0446, the 0.0446. Since this is a one-tail test, the p-value is the size of this green corner. So p-value is 0.0445. It's just marginally smaller than 0.05. So it is smaller than alpha. We should reject the null hypothesis, but also we realize that for this alpha level that we set at 0.05, this particular sample mean is marginally significant because it's just slightly smaller than 0.05. Okay. So we realize that this sample mean 33.3 is significant for the alpha level we set up, but it's only barely significant for the level of significance we set for this question. So not extremely, it is rare, but not extremely rare because it's just barely lower than the alpha that we set as the standard of gray event for the given null hypothesis. So for this question, we conclude that we reject the null hypothesis. The population mean is significantly younger than 35 at the 5% level.